video accompanies our work, Game-theoretic occlusion-aware motion planning, and efficient hybrid information approach. Consider the situation on screen. The green car wishes to overtake a slower blue car. At this moment, the oncoming brown car is occluded from its view. This example highlights a core challenge in motion planning. The ability of an agent to predict or reason about behaviors of other agents is compromised in the presence of occlusions, leading to potentially unsafe trajectory planning. Dynamic game theory provides a suitable formalism for motion planning problems involving multiple decision-making agents, avoiding requiring an agent to make a priori predictive assumptions about others. There are three ingredients to a dynamic game: A, the dynamics, B, the cost, and C, the information structure. The choice of information structure is critical because in a dynamic game, the decision made by each agent affects decisions made by all other agents, and consequently, the game's solution. Feedback assumes knowledge of states of all players at the current time step, while open loop assumes only the initial state of all agents to be known. In our work, we use feedback to model periods of visibility and use open loop to model periods of occlusions. Note that the output matrices of both feedback and open loop solutions depend recursively through time and utilize the input terminal costs for each player. As an illustration, consider alternating periods of visibility and occlusions. At the end of an occlusion, we model agent's terminal costs as the optimal cost to go from the next visible state, and similarly treat times when a period of visibility ends. A complete framework is an iterative scheme which employs this hybrid LQ algorithm to identify approximate Nash equilibria in non-LQ games. Our simulation of a three-player scenario results in successful overtaking trajectories. Note that our computational time is significantly lesser than the previous state-of-the-art methods. Observe that in comparison to an overly cautious pure open-loop baseline, our method does better while also being correctly less confident than an unrealistic pure feedback baseline. In this two-player scenario, the orange and green cars are occluded and initially set to collide. Notice how at the intersection, the orange car zooms past. To do so, it successfully reasons to change its velocity during the occlusion period.